Hello all, I just want to first time share my video with full English. I am just trying to share this video in full English language, total English. So I am just introducing you to the probability distribution. Probability distribution function, there are discrete probability distribution function, continuous probability distribution function, and sampling distribution function. I am just covering here probability distribution function continuous and discrete only. I am just hoping you all guys have read well in the textbooks all these distribution function, and you are just lacking skill of remembering it. How to remember all this distribution? My answer is you just have to write down it and wrote it. I haven't any magic wand that I will that can help you to remember all this. Though I have just written, I am just suggesting you, if you want to remember these probability distribution functions properties, just write it down like this. These only one page have all 6 discrete probability distribution function. Let me show you. X minus a upon b minus a. What is it? It is the discrete probability function, discrete probability distribution function. No, it is continuous. It is continuous probability function, rectangular function. Rectangular functions probability density function. This is x minus a upon b minus a. This is the distribution function of the rectangular distribution. Then b plus a by 2. What is this? This is just mean of rectangular distribution function. B minus a upon all square, b minus a all square upon 12 is variance of the rectangular distribution function. E raised to tb minus e raised to ta upon tb minus ta. What is this? This is just a moment generating function of a rectangular distribution function. 0 is the skewness of the rectangular distribution function, and 9 by 5 is the kurtosis. This is beta 1 and this is beta 2. If you just want to find not beta 2 but gamma 2, this is kurtosis, then just subtract 3 from 9 upon 5. Still it will remain platy-kurtic, right? So this distribution, rectangular distribution, is symmetric. Why? Its beta 1 or gamma 1 is 0. While it is 0, the distribution function is symmetric. And this is beta 2, or yes, beta 2, and this is greater than 3, because 9 by 5 will no, it's not greater than 3. 9 by 5, okay, 9 by 5 is not greater than 3, so it's platy-kurtic. I think it's symmetric and platy-kurtic. Mean and median are same, b plus a by 2, in this rectangular distribution function, and mode doesn't exist for rectangular distribution function. One more property which we are not covering for our distribution: mean deviation about mean is b minus a by 4 in this rectangular distribution function. And if x is a continuous random variable of rectangular distribution function, then minus 2 log x will follow chi-square distribution function with 2 degree of freedom. Okay, that's clear. And if x is a continuous random variable of rectangular function, then minus 2n log x will follow also follow chi-square distribution function with 2n degree of freedom. You must have read it somewhere in your textbook if you are a student of probability, student of statistics. I am not just a student of statistics, but I have to give such an exam after 10 days, so I am preparing all for this. I am new, but though if you are a full-time statistical student, then it will help you to just remember. I have sorted out a nice way to remember all this distribution. So I haven't written of which distribution this property is, lambda e raised to minus lambda x. Because you have to remember, when you see this sheet, you have to remember which distribution this is, which property is this. Is this a probability distribution function, or is this mean, or is this variance, or is this skewness? Nothing has written, but you have to remember it. That will give you more power to remember this by this sheet. So PDF, a probability density function of exponential distribution is lambda e raised to minus lambda x. If you are giving objective exam, then please remember, if you are being asked about distribution, cumulative distribution function of exponential distribution, then it will not be lambda e raised to minus lambda x, but it will be 1 minus e raised to minus lambda x. So remember, in exponential distribution, probability density function is lambda e raised to minus lambda x, and probability distribution function is 1 minus e raised to minus lambda x. Skewness is 1 upon lambda. Mean is 1 upon lambda. Variance is 1 upon lambda square. Skewness is 4. Kurtosis is 9. Hence, exponential distribution is both what you call it, more than symmetric, is in skewness is positively skewed, and it is platykurtic. Hence, beta 2 is equal to 9. So, gamma 2 is equal to 6. And when beta 2 greater than 3 or gamma 2 is greater than 0, then you will find its kurtosis is platykurtic. Then, of exponential distribution, these all property, this all line is about exponential distribution. So, what is this? Which this property is lambda by lambda minus t. Which property is this of exponential distribution? Okay, now I am putting it right in English. Which is this property of exponential distribution? Lambda upon lambda minus t is moment generating function. You say mx of t or mgf. Moment generating function of exponential distribution, lambda by lambda minus t. One thing more to remember, exponential distribution has a memoryless property. Only two distribution, exponential and geometric. While geometric is a discrete distribution, and exponential is continuous distribution. So, though exponential and geometric, only two have the memoryless property. Then we move forward. After exponential distribution, we are seeing it double exponential distribution. So, distribution function of the double exponential distribution function is 1 half into lambda into e raised to minus lambda into mod x minus mu. So, just compare both these distribution function of exponential distribution and double exponential distribution. In exponential distribution, it is lambda e raised to minus lambda x, and in double exponential distribution, it just adds or multiply with 1 half. 1 half into lambda e raised to minus lambda, not only x, but into mod x minus mu. So, while mean is 1 upon lambda in that exponential distribution, double exponential distribution has one more parameter. Exponential distribution has only one parameter, lambda. Double exponential distribution has two parameters, lambda and mu. So, mean is mu, just like normal distribution. We see mu is the mean of normal distribution, also of double exponential distribution. You just see another similarity. This all line is for normal distribution. Both are symmetric. Just see, rectangular distribution has also skewness 0. Double exponential distribution just have also skewness 0, and normal distribution have also skewness 0. So, three of them are symmetric. So double exponential distributions, skewness is 0, mean is mu, variance is 2 upon lambda square, while in exponential distribution variance is 1 upon lambda square. In double exponential distribution variance is 2 upon lambda square. Kurtosis is 6. Moment generating function, while we have seen that in exponential distribution moment generating function is lambda upon lambda minus t, and in double exponential distribution we have moment generating function is lambda square upon lambda square minus t square into e raised to mu t. So it's kind of similar with exponential distribution. Exponential distribution have moment generating function lambda upon lambda minus t. So we are seeing square of all each individual, lambda square, lambda minus t. In place of lambda minus t, we are have in lambda square minus t square, and this term is multiplied by e raised to mu t. We are seeing one more property, Q3 minus Q1. This is interquartile range. If you were asked the interquartile range of double exponential distribution, just say them it's 2 log 2 upon lambda. Okay. So now we are moving toward the normal distribution. Normal distribution has distribution function is 1 upon sigma under root 2 pi into e raised to minus 1 half into z square. Now what is z? Z is equal to x minus mu upon sigma. If you are the student of statistics, you know how to standardize any distribution into normal by standardize any normal distribution into standardized normal distribution by moving its variable x and mu into z, plotting. It's called plotting. I don't know much about it because exam which I am going to give has no much will not give me much time to calculate this calculation. So I am not focusing on this descriptive measure, but you can know z is equal to x minus mu upon sigma. You can plot x or your x and mu as required by in the z. Okay, so z is equal to x minus mu upon sigma. That will shorter your term to remember, because you just only need to remember 1 upon sigma under root 2 pi into e raised to minus 1 half into z square. Now you can remember this separately. What is z? Z is equal to x minus mu upon sigma. So you have to write, or you have to select from option square of all these, x minus mu all square upon sigma square in this equation of normal distribution. So this is a distribution function of normal distribution. Mean of normal distribution function is mu, variance is sigma square, skewness that is beta 1 is equal to 0, kurtosis that is beta 2 is equal to 3. So hence normal distribution have skewness is beta 2 is equal to 3, and if we see gamma 2, so it's less than 3, then beta 2, so it's also 0. So beta, gamma 1, gamma 2, all both are 0. Skewness 0, kurtosis 0. This is measure of beta 2, that is 3. So if beta 2 is equal to 3, then this distribution, this normal distribution will be called symmetric. If beta 1 is equal to 0, then it's symmetric, and if beta 2 is equal to 3, so it's not a mesokurtic or platykurtic, but in between what it says, I just forgot. Symmetric. Yes, no, symmetric is for skewness, and what is for kurtosis? Mesokurtic, platykurtic. So okay, all right. It's not its bell shape is not much higher or much dwarf. Okay, so it's of medium. Now moment generating function of normal distribution is e raised to mu t plus 1 half into sigma square t square. So it is kind of tricky to remember. Moment generating function of normal distribution is e raised to mu t plus 1 half sigma square t square. Okay. And if x and y both follows a normal distribution, if we have two continuous random variable x and y which both follows a normal distribution, then x upon y will follow what? That will not follow normal distribution, but x upon y will then follow Cauchy distribution. So it is one more thing to remember. Normal distribution, we have a mode at x is equal to mu. When we put value of mean in any point, we will find the mode of normal distribution. Now we are moving forward to log normal distribution. Log normal distribution is 1 upon x into sigma upon under root 2 pi. While we have this first part of this term of normal distributions distribution function have only 1 upon sigma under root 2 pi, but here we have additional x multiplied with it. 1 upon x into sigma under root 2 pi into Sm as that was in normal distribution, e raised to minus 1 half, e raised to minus 1 half. Then we have x minus mu upon sigma all square over in normal distribution, but in log normal distribution just replace x with log x. Okay, so you have to just put one x with sigma into under root 2 pi and just replace x with log x in that power of e. So this is the distribution function of log normal distribution. Let me say it again. 1 upon x into sigma under root 2 pi into e raised to minus 1 half into log x minus mu upon sigma all raised to 2. Now we have moment generating function. No, it's mean of log normal distribution is e raised to mu plus 1 half sigma square. It is kind of looking like a moment generating function of normal distribution, but its mean of log normal distribution is e raised to mu plus 1 half sigma square. And this is variance. Variance of log normal distribution is e raised to 2 mu plus sigma square into e raised to sigma square minus 1. Guys, that is too much. That is too tricky to remember. But what to do? You have to remember log normal distribution is both positively skewed and leptokurtic. Okay, it is more skewed, and it has high kurtosis. So it is positively skewed and leptokurtic. Okay, I was just forget to mention you. I just did not getting it remember that in normal distribution the kurtosis we can call it mesokurtic. Okay, if beta 2 is equal to 3, then it's mesokurtic. If beta 2 is greater than 3, then it is leptokurtic, and if beta 2 is less than 3, then it is platykurtic, as you all know. Now we are moving forward to relationship with another distribution function. We have seen that in normal distribution, if x upon y, if both x and y are following a normal distribution, then x upon y will follow Cauchy distribution. So in log normal distribution, x plus y, make it x into y, or say it x minus y, or just divide both of them and make it x upon y, all remain same log normal distribution. That doesn't transform into another distribution. So that is another thing to remember about log normal distribution. But guys, mean and variance of log normal distribution is I am finding hard to just remember it. So please comment and tell me how to remember all this. So last in this continuous distribution. No, it's not last. It can't be. This is Cauchy distribution. Cauchy distribution, probability density function of the Cauchy distribution. 1 upon pi beta into 1 plus x minus alpha upon beta whole square. This is the distribution function of the Cauchy distribution. And the beauty of the Cauchy distribution, it doesn't have variance or moment generating function exist. Wow. So you don't have to remember it. It have a mode at its x is equal to infinite. If you put, sorry, it may be alpha. If you may put x is equal to alpha, then you will get a mode of it. As it haven't a moment generating function. But one thing to remember, I just want to remember you, all function which doesn't have moment generating function, but they at least have characteristic function. So characteristic function of Cauchy distribution is e raised to I alpha t minus beta of mod t. So e raised to I alpha t minus beta into mod t is the characteristic function of the Cauchy distribution. Now points of inflection. This is another thing to remember, points of inflection. Points of inflection means when you draw a graph, then when it suddenly goes up or down, so that particular point are called points of inflection. So points of inflection of Cauchy distribution is alpha plus 1 upon under root 3 beta and alpha minus 1 upon under root 3 beta. That's okay to remember. That was easy. Now we are moving forward. Which distribution is this? 1 upon beta a b. Guys, you have read it different terms in different books. Some book says 1 upon beta into alpha beta, 1 upon beta m, and whatever you say, just stick to only one term. I am just sticking calling it a and b. 1 upon beta of a and b into x raised to a minus 1 into 1 minus x raised to b minus 1 is the distribution function of beta 1 distribution. There are two beta kind of distribution, beta first kind, beta second kind. This is the beta first kind. So remember it. How do I remember this is a beta kind, first kind? Remember because I have write it first, then I have written down it beta 2, beta second kind of distribution. So I am so I just know this is beta first kind, this is beta 2. But when in exam where I haven't written question, that can make me confused. So I need to practice more to remember these all properties of distribution function as well you. So mean of beta first kind distribution is a upon a plus b. Variance of the beta first kind distribution is a into b upon a plus b all square into a plus b plus 1. This is variance of the beta second kind distribution. Now harmonic mean. One more weird thing to remember is harmonic mean. Just deduce, just put minus 1 in both up and down in this mean. A minus 1, a plus b minus 1. Then you get harmonic mean. See, the mean of a beta first kind distribution is a upon a plus b, and harmonic mean is a minus 1 upon a plus b minus 1. So this is mean, this is variance, this is harmonic mean. Now characteristic function of beta of first kind distribution is 1 upon beta ab into sigma j is equal to 0 up to infinite, summation of j is equal to 0 up to infinite it raised to j upon j factorial into beta of a plus j and b. So this is kind of like a distribution function. This is more than long than distribution function, as I can see. So this is characteristic function of beta first kind distribution. So beta first kind distribution have mode at x is equal to 0 if sorry, I have written it in Gujarati, but I am just translating for you what I just mean to say. Beta of first kind distribution have mode at x is equal to 0 if a is smaller than b. If a is smaller than b, then mode will have at x is equal to 0. If b is smaller than a, then mode will be at x is equal to 1. In textbook, just see you have so much cases. While a is equal to 0, b is equal to 1, mode will be at where? So mode will be at x is equal to 0. If a is equal to 0 and b is equal to 0, mode is equal to where? Mode will be both as x is equal to 0 and x is equal to 1. If a is equal to 1, b is equal to 1, where will be mode at? Mode will be at every point x is equal to every point in beta distribution. If a is equal to 1 and beta if a is equal to 1 and b is greater than 1, then mode will be at where? Mode will be at x is equal to 0 as a is smaller than b. So just remember, when a is smaller, then mode will be at x is equal to 0. When b is smaller, mode will be at x is equal to 1. Where in beta of first kind distribution. If you will be asked about mode in beta first kind distribution, then just remember this trick. Now we are moving forward in beta second kind distribution. 1 upon beta of ab into x raised to a minus 1 upon x plus 1 raised to a plus b. Just compare both these distribution function. This is distribution function of beta of first kind, and this is the distribution function of beta of second kind. Beta of second kind have distribution function is like 1 upon beta of ab into x raised to a minus 1 upon x plus 1 raised to a plus b. So both were similar till that 1 upon beta ab into x raised to a minus 1. Okay, both were same till that time, but after that it doesn't have 1 minus x raised to b minus 1. In place of it has x plus in under x plus 1 raised to a plus b. So mean of the beta of second kind distribution is a upon b minus 1, and variance, it's a hard variance, a into a plus b minus 1 upon a minus 1 square into b minus 2. Leave that, guys. I am not gonna remember this variance of beta of first kind distribution and beta of second kind distribution. It's hard for me. But harmonic mean is a minus 1 upon b. That will also confuse me. Harmonic mean of beta 1 distribution is a minus 1 upon a plus b minus 1. Harmonic mean of beta of second kind is a minus 1 upon b. Characteristic function is also weighed 1 upon gamma of a into gamma of b into summation of k is equal to 0 up to infinite it raised to k upon k factorial. That is similar for both beta characteristic function of beta of first kind and beta of second kind. That it raised to something upon that something factorial, it raised to j upon j factorial, it raised to k upon k factorial into gamma of a plus k into gamma of b minus k. That's too much. Characteristic function of beta of first kind and beta of second kind. See these both and compare it. Now we have last gamma distribution. The cumulative density function of gamma distribution is beta raised to alpha upon beta raised to alpha upon gamma of alpha into e raised to minus beta x into x raised to alpha minus 1. So this is a cumulative density function of the gamma distribution. Mean is alpha upon beta and variance is alpha upon beta square. And mode, you will find its mode at alpha minus 1 upon beta, and if alpha is less than 1, then its mode will be 0, but not in minus. So this is the mode of gamma distribution at alpha minus 1 upon beta. Now this is a MGF, moment generating function of gamma distribution is beta upon beta minus t all raised to alpha. So it's positively skew and leptokurtic, and it have so much too much relationship with the other distribution. If alpha is equal to 1, it turns into exponential distribution. Exponential distribution, which we have earlier seen. This is exponential distribution. Yes. Moment generating function of exponential distribution is lambda upon lambda minus t, while moment generating function of this gamma distribution is beta upon beta minus t. So both is similar, and but it only have a power of alpha in its moment generating function against that moment generating function of exponential distribution. See, exponential, yes, it have more power alpha in gamma distribution. So if in gamma distribution, if that alpha is equal to 1, then it will be turned in a similar moment generating function, and it will turn into a exponential distribution. That was I trying to say. If alpha is equal to 1, gamma distribution turns into exponential distribution. If x and y both are continuous random variable that follows gamma distribution, then x plus y also remains gamma distribution. But in that case, x upon x plus y will turns into beta of first kind, and x upon y will be turned into beta of second kind. So that was all of continuous distribution. This is a distribution function, rectangular distribution function. This is exponential. This is double exponential distribution function. The property of double exponential distribution function. These are the properties of normal distribution function. These are the property of log normal distribution function. These are the properties of Cauchy distribution function. These are the properties of beta distribution of first kind. These are the property of beta distribution of second kind, and these are the properties of gamma distribution. So now let's we turn to distribution function that are discrete probability distribution function. So what is this? P raised to x into q raised to 1. It is much easier than that lengthy continuous distribution functions properties. This is p raised to x into q raised to 1 minus x. This is a probability mass function. See, we were calling it cumulative distribution cumulative density function for continuous probability distribution function. But when probability functions are discrete but not continue, then their distribution function will called probability mass function. P raised to x into q raised to 1 minus x is a PMF of this distribution function. This is Bernoulli distribution function. James Bernoulli found it. Then its mean is p. It have only one parameter p. Q is not its parameter because q is equal to 1 minus p. So it has only one parameter p. Variance is pq, and moment generating function is q plus p e raised to t. Then we move forward to binomial distribution, NCx into p raised to x q raised to n minus x. Just compare it to Bernoulli distribution. It will help you to remember it both together. Then mean of the binomial distribution is NP, variance of the binomial distribution is NPQ, moment generating function of the this binomial distribution is similar to that Bernoulli distribution, Q plus P e raised to T, that is Q plus P e raised to T all raised to N. So think about it. Just you put n is equal to 1, it will turn into moment it will turn into the moment generating function of a Bernoulli distribution. So let's see, I have written here, if n is equal to 1, this distribution function, binomial distribution function, will turn into Bernoulli distribution. Okay, so we also call Bernoulli distribution a point binomial distribution. Thing to remember. And then we see skewness. Skewness is equal to 1 minus skewness. We say beta 1. Okay, beta 1 is equal to 1 minus 2p all square upon npq. And if we seeking for gamma 2, not beta 2, then it is 1 minus 6pq upon npq. But in case of beta 2, just add 3 in this term and you will get beta 2. So beta 2 is equal to 3 plus 1 minus 6pq upon npq. 3 is not in that numerator, denominator. Yes. I was just forgetting Ans and Ched is called numerator and denominator in English. Okay, I was just trying to tell you about in last part that we see in continuous distribution function, but not remembering that term, that numerator and denominator. So 3 is not in numerator. 3 is I have just mistakenly written that line. 3 plus now this line start after to this line 1 minus 6pq upon npq is the variance, sorry, is the kurtosis of the binomial distribution, and skewness is 1 upon 1 minus 2p all square upon npq. Now this is recurrence formula. If we have a formula of p of x, and if we are founding formula of p of x plus 1, then p of x plus 1 is equal to all this. P of x plus 1 is equal to p of x into p upon q into n minus x upon x plus 1. Remember this term, n minus x upon x plus 1. This will repeat once again in n minus x upon x plus 1. This is hypergeometric functions recurring formula. That also have this term, n minus x upon x plus 1. So recurrence formula for the binomial distribution is p of x plus 1 is equal to p of x into p upon q into n minus x upon x plus 1. So if n is equal to 1, then binomial distribution turns into Bernoulli distribution. If n tends to infinite and p tends to 0, means sample size is so large and probability of success is so low, then it turns into Poisson distribution. X plus 1 remains binomial, means if x and y both follows binomial distribution, then x plus y remains binomial. But in Poisson distribution, if x and y both follows Poisson distribution, then x plus y turns into binomial distribution. That we will see in later in this Poisson distributions property. Now PMF of Poisson distribution, probability distribution of this Poisson distribution is e raised to minus lambda into lambda raised to x upon x factorial. Mean is lambda, variance is also lambda. Moment generating function is something tricky, but remember, e raised to lambda into e raised to t minus 1. E raised to lambda into e raised to t minus 1 is the moment generating function of this Poisson distribution. Then skewness and kurtosis both are same, 1 upon lambda, 1 upon lambda. And this is both are platykurtic and what you say above symmetric, higher than symmetric is positively skewed and platykurtic both is. Recurrence formula for Poisson distribution is P of x plus 1 is equal to all this. P of x plus 1 is equal to P of x into lambda upon x plus 1. If x and y both follows Poisson distribution, then x plus y follows binomial distribution, and x minus y follows neither binomial neither Poisson. X minus y doesn't follows Poisson distribution. Just this is remember. Now this is negative binomial distribution. Negative binomial distribution. What is another name of negative binomial distribution? Just name it in the comment section. X plus r minus 1 c r minus 1. What is x plus r? X plus r is the whole number of trial with success and without success is x plus r. X plus r minus 1 upon r minus 1. Sorry, not upon, x plus r minus 1 c r minus 1 into p raised to r into q raised to x. See, r of number of trials that doesn't succeed, and x is the number of trial that get succeed. If a marker shoots the, if shooter shoots shoots in the right time 2 times out of 6 times, then r is 4 and x is equal to 2. That is somewhat you can understand. RQ upon P is its mean, and RQ upon P square is its variance. What is Q? Q is equal to P minus 1. P is probability of success, Q is probability of failure. RQ upon P is mean, RQ upon P square is variance. Now that is tricky. Capital Q minus P, capital Q minus capital P e raised to T all raised to minus r. What is Q and P capital? So remember, we have got Q plus P e raised to T all raised to n, but here Q minus P e raised to T all raised to not n, but raised to minus r, and it's not plus, but in place of plus it's minus. So it is somehow similar to a binomial distribution. This is the moment generating function of negative binomial distribution is. But see that capital Q is equal to 1 upon P. P is probability of success, and this capital P is equal to 1 minus Q. So these are the additional things you have to remember. So you can get this moment generating function in terms of the small p and q also. If you put 1 upon p in place of capital Q, and you put 1 minus q, 1 minus this capital Q in place of this capital P. So skewness is equal to capital Q plus P all square upon R capital Q capital P. This is this is Q plus P all square upon R cube P is skewness, and kurtosis is 1 plus 6 PQ upon R PQ. Recurrence formula for this negative binomial distribution is f of x into Q into x plus R upon x plus 1. So in binomial distribution, we had recurrence formula that similar function p of x into not q but p upon q into n minus x upon x plus 1, while here is x plus r upon x plus 1. So there is r in place of n, and there is not subtraction but addition in that this negative binomial distribution x plus r upon x plus 1. Yes, both have x plus 1 in this denominator. Now if r is equal to 1, if r is equal to 1, then it turn into geometric distribution. Now geometric distribution, PMF of geometric distribution is PQ raised to X, mean is Q upon P, variance is Q upon P square. As we see, mean of a negative binomial is RQ upon P and RQ upon P square. But if R is equal to 1, then its mean will be, put R is equal to 1, Px. Okay, put them all in R is equal to 1 in this formula. You will get 3 of this formula. PQ raised to X, RQ upon P is, if R is equal to 1, then it's Q upon P. This is mean of geometric distribution. RQ upon P square is variance of the negative binomial distribution. If you put R is equal to 1, it will become Q upon P square, and Q upon P square is the variance of the geometric distribution. Moment generating function is the minus log 2 upon, no, it's not moment generating function, it's median. Median of geometric distribution is minus log 2 upon log 1 minus p, and you will find its mode at x is equal to 0. Let me ask you a question. When you find a mode of the normal distribution, when you put x is equal to mu, okay, but in this geometric distribution, you get x is you get its mode by putting x is equal to 0 in the formula. Moment generating function is equal to p upon 1 minus q e raised to t, and this is hypergeometric distribution. Kcx into n minus k upon n minus x, kcx into n minus k c n minus x upon capital N c small n. What these all are? See, capital N is number of total population. Small n is number of population, is the number of samples we have collected from the total population. So total population of the sample, you can say, so small n is the total population of the sample. Capital N is total number of total population. Now k is number of success, and x is number of success in that sample that we have taken, number of small n. So now see, what is this? Kcx minus sample success out, minus sample success out of total success. So you can also read it like total success C sample success. Now what is capital N minus K? See, capital N is number of total population and K is number of success in total population. N minus K is number of failure. N minus K is number of failure in the total population. So number of failure in total population, C number of failure in sample population, upon number of total population, C number of sample population. So again, translating it in English, this mathematical formula is total success C sample success into total failure C sample failure, and total number C sample number. So this is distribution function of hypergeometric distribution, and this is mean NP, and which also have a mean NP. Binomial distribution have mean NP, and binomial distribution have variance NPQ. These also have hypergeometric distribution, also have mean NPQ, but multiplied with capital N minus small n upon capital N minus 1. Recurrence formula is f of x into n minus x upon x plus 1. See, this term was also in binomial distribution, as I earlier said. And what is this term? This term is simple. See, kcx, just for sake of remembering, I am telling you just k minus x. Make it k minus x. Kcx to k minus x. Now subtract this from this. Subtract n minus k minus n. If you put minus in this forward to this term, then this minus will get plus. So just for sake of remembering, say it n minus k minus n plus x plus additional 1 plus 1. uh, as if we putting x plus 1 here, also see x plus 1 here, just for sake of remembering. So this is recurrence formula of hypergeometric distribution. F of x plus 1 is equal to f of x into n minus x upon x plus 1, similar term that was in binomial distribution, into k minus x upon n minus k minus n plus x plus 1. And if n tends to infinite, this number of total sample are so much higher or infinite, then it turns into binomial distribution. This is hypergeometric. So that was it, guys. This was the Bernoulli distribution. Then we have C property of this binomial distribution. Then we have seen the properties of this Poisson distribution. Then this is this is property of negative binomial distribution. And this is the property of geometric distribution, and this is the property of hypergeometric distribution. Again, just remember what we have learned in continuous distribution section. This is the property of rectangular distribution, continuous rectangular distribution. This is property of the exponential distribution. This is double exponential distribution. This is normal distribution. This is log normal distribution. This is Cauchy distribution, and this is the property of beta of first kind, beta of second kind, and lastly gamma distribution. So we have covered all important, not all, but all which are important continuous and discrete distribution functions property. Sampling distribution functions are not covered here. If I had tried to cover it, the video will have become so exhaustive to watch. Bye bye. Thank you.